Putting together pieces in a design that is simple and beautiful. And that's what nature has really provided us with.
Energy needs to be captured fast. If we want to study something that fast, we need something even faster. And the only way to do that is through light.
Discovering something new, and then realizing that not only is it new from a scientific point of view, that it's going to change science, but if possible, it can also change technology.
If we're born to be able to learn language, it's our native language we have to acquire, and perception is the gateway through which we learn about our native language.
You have to have a thick skin in biology or in any field where you're putting yourself on the line. You got to do something bigger than just you. You got to do something that's so meaningful, will have a big impact.
The future of tech is incredibly exciting right now. I like to believe that technology is actually making our lives much better, much more productive, and much more enjoyable, and that's what I view as a success.
The ability to create something new that has a specific function. It's like working with a puzzle, and you're thinking to yourself, how can I build something that will actually address that need?
We wanted to call it something that would admit to variation in the future. So we chose that word, ether, an omnipresent passive medium for the propagation of electromagnetic waves, Ethernet.
We can take a jug of specimens, extract DNA from the jug, and read the species in it. And that's what science is all about, making things that were absolutely impossible possible.
Good evening. I'm Larry Benson, President and CEO of the Franklin Institute. The individuals you just saw on your screen are all members of the Franklin Institute Awards class of 2024, with exceptional accomplishments in fields ranging from materials engineering to plant biology to language acquisition. They will each be honored at the Bicentennial Award Ceremony next Thursday, April 18th. The laureates join a remarkable 200-year-old legacy that includes many giants of science history: Marie Curie, Nikola Tesla, Orville Wright, Albert Einstein, Stephen Hawking, and modern greats like Jane Goodall, Bill Gates, Katie Carrico, and Drew Weissman. With a mission to inspire a passion for learning about science and technology, the Franklin Institute is proud to be the most visited museum in the Commonwealth of Pennsylvania and a national leader in STEM education. The Science Center has been bustling with activity this spring, from visitors enjoying our special exhibit, Art of the Brick, to kids and families experiencing our newest and international award-winning exhibit, Wondrous Space, for the very first time. But science just isn't happening inside of TFI's walls. On Monday, we hosted a free community-wide solar eclipse viewing party with sun spotters, solar filtered tents, and specially equipped telescopes. 8,000 people came out, standing shoulder to shoulder on the Franklin Institute's front steps and front lawn and up and down both sides of 20th Street. The energy was incredible as our chief astronomer, Derek Pitts, guided everyone through the stages of the eclipse. We also collaborated with several youth-serving organizations in Philadelphia to host solar eclipse parties in neighborhoods across the city. This work was a part of TFI's Mission to Mars program, carried out in partnership with NASA. And now, TFI's programming makes its way to the virtual space with a discussion that kicks off a series of events that are part of the Bicentennial Awards program. Tonight's panel features 5 2024 laureates who will engage us in informative discussions around their exceptional achievements in science and engineering. Awards programming reaches its pinnacle next Thursday at the Bicentennial Awards Ceremony and Dinner, when our remarkable laureates will accept their awards at a grand ceremony at the Franklin Institute and the Benjamin Franklin National Memorial. We are grateful for our longtime presenting sponsor, Bank of America, and our 200th anniversary sponsors, the Hess Foundation, PNC Bank, and UST for making these events possible. Guiding the conversation tonight is our Chief Bioscientist, Dr. Jayatri Das. Thank you for joining us this evening. Jayatri, I turn it over to you.
Thank you, Larry. And thanks to all of you for joining us for what promises to be a really exciting and dynamic conversation tonight. One of the things that really jumped out to us as we were learning about the science that all of this year's laureates are doing is how interdisciplinary this work is. So often we think about a focus on one topic or another topic, but today, as we learn about their work, I hope you'll have the chance to understand and appreciate the interdisciplinary nature that all of our scientists tonight are making by building bridges across fields and with each other. We hope that you'll find connections to each of their lives and perspectives as they share some of the stories behind their work and their accomplishments. And we hope that you'll be inspired by advice on how to pursue your own passions and interests in STEM. So it's really exciting to be kicking off this year's Bicentennial Awards Week with these incredible laureates. I'd like to ask them to join me on our virtual stage tonight as I introduce each of them. So please go ahead and come on camera. We're joined tonight by Dr. Paula Hammond from the Massachusetts Institute of Technology, who will be receiving the Benjamin Franklin Medal in Chemistry. Dr. Janet Worker from the University of British Columbia will be receiving the Benjamin Franklin Medal in Computer and Cognitive Science. Dr. Joanne Corey from the Salk Institute for Biological Studies is our Benjamin Franklin Medal in Life Science. Dr. Mary Boyce from Columbia University is awarded the Benjamin Franklin Medal in Mechanical Engineering. Finally, Dr. Gabriella Schlau-Cohen from the Massachusetts Institute of Technology is the recipient of our Benjamin Franklin Next Gen Award. So thank you so much to all of you for joining us tonight, and I'm excited to dive in with our first lightning round question. We're aiming to have a very dynamic conversation tonight. And so for our audience, we gave all of our laureates some props to facilitate the dialogue as we go along. And our first lightning round question is, let me get that on stage here. When I was in high school, I dreamed of becoming and you can each hold up your orange card to show us what you. All right, so we've got a rock and roll star, an ethologist, an actress, a physicist, and a fiction writer. Amazing. So Joanne and Gabriella, you both clearly had a stage presence early on. Can you tell us a little bit about, what motivated that?
No, I can't actually. I mean, I don't think I had a stage presence as a young person, but I did really like rock and roll. I love music, and so I would always be singing, and playing air guitar and doing that kind of thing. But yeah.
Love it.
Okay.
What about you, Gabriella?
I think I just thought it was fun. People talk about a performance high, so it was fun getting up there, pretending to be something else, getting lost in a story.
So Paula, as a fiction writer, you clearly thought about stories as well. What was motivating to you at that time?
At that time, I loved books. I read books all the time. I would skip anything if I could get a chance to read. And I loved children's fiction, and I decided that I was going to write books, either be like Beverly Cleary or, some of the other famous authors, maybe even science fiction, children's science fiction.
And Janet and Mary, you clearly had your paths laid out for you from the very beginning. How did you acquire that focus so early on? Oh, go ahead, Mary. I think we're not quite hearing you.
I always loved the mathematics and the geometry, algebra, calculus, and then when I took physics, I realized it was all sort of directed to understanding the world. And I had never heard of what an engineer was. So I never dreamed to be an engineer because I didn't know what an engineer was. But it all came together in college. But the sense that physics kind of gave meaning to this mathematics that I loved. That's sort of why it was there.
And Janet, how about you? I don't think I even knew what an ethologist was until I was in graduate school.
Yeah. So an ethologist studies animals in their natural environment. And I have an older brother who's 9 years older than I am, and he was in grad school at Stanford, and I went out to visit him. And being from a small town, he gave me a shopping cart and told me to go through the Stanford bookstore and just fill it with books, and that he was going to buy all those for me. And among those books were books by Conrad Lorenz, Nico Tinbergen, the forefathers of Jane Goodell. And that's what I fell in love with. And I wanted to do that. I wanted to study animals in their natural environment.
I love that about how listening to all of your stories about, you know, what you saw in the world around you, what interested you, and thinking about how you connected those threads to where you are today. So that takes us to our next exercise, when we're going to dive a little bit more into what each of your research focuses on. And we're calling this activity Your Science Made Simple. So one of my favorite tools in explaining science to people and making sure that we start at a level that almost everybody can understand is to use a tool that has a filter that gives you a little alert when you're using the 1,000 most common words in the English language. This is a tool that gives us this first round of explanation. But as we'll see, it might be almost a little bit too simple to really appreciate the connections between what you do. So we're going to start with your simple science and use that as a starting point. We're then discussing a little bit more about the kind of techniques that you do, the questions you ask, and hopefully the impact that it has as well, and try to find some of these connections between your work. So, Gabriella, you are up first. You study how green living things keep themselves safe from the sun. We can use your work to figure out how these green living things can grow bigger and faster to make more food for people. So first, obviously, the word plants is not one of the 1,000 most common words in the English language. But Gabriella, build on this. What do you like about this? What does it miss? And then tell us a little bit more about what you do.
All right. Well, I like how simple it is and how it gets to the idea of what we're studying. It misses a little bit about the how, what tools we use to look at that. We use lasers and microscopes, which probably are similarly not among the 1,000 most common words in the English language.
So tell us a little bit more about the lasers and microscopes and how that helps you answer sort of the more detailed questions that you're asking.
Yeah, so we're interested in how plants keep themselves safe from particularly changes in sunlight. There's clouds, there's shadows, and how they respond to that. And we're interested in the very first steps of photosynthesis, the process by which plants use light energy to grow. And we use lasers to kind of be like the sun, to use light similar to the sun, but in a controlled way. So we can see what happens when we use a laser to excite our system. And then we use a microscope because we're really interested in the protein level mechanisms, not just what's happening to the plant as a whole, but I'm a chemist. So we zoom into the molecular level. And the microscope is part of how we do that, so that we can use the microscope to get at the protein level behavior and see how the proteins and how they interact with light changes under different conditions.
And that's all happening at such a fast level that that light is really what helps you capture that at speed.
Yeah, well, plants are up against a clock. They absorb that light and they have just a few nanoseconds, 10 to the negative ninth of a second, to use that energy from light or lose it. So they got to use it or lose it. And so they have a lot of really fast things by which the energy moves around. So it can be converted into electricity and then into chemical stocks.
All right, so the other four of you, thumbs up, thumbs down for seeing connections to Gabriella's work. All right, Mary, you go first. Tell us what you see.
All right, so do we put up my simple statement? To comment on Gabriella and how it connects. Okay. So I see the connection because in my work, I really am looking at the molecular structure of polymeric materials, natural and synthetic, and how that molecular structure enables the large deformations and really mechanical properties to create new things, whether it's the next generation sneaker. We see lots of things happening with sneakers now. If it's the tire designs, if you watch Formula One, there's a lot going on in these soft, hard tires that they don't say, but are actually what the winning part of a race. If you look at natural structures such as spider webs, muscle bistle threads, even our tissues in our body, we're looking, quite similarly when we think of what Gabriella was saying, is how does the molecular structure and other microstructure, it could be other particles or other entities in the material, build up to actually give the behavior. And the kinds of tools you can use is also, I think, opening up avenues that none of us, back when we were undergraduates, would have even thought possible, right? And it's not just experimental, it's also computational. The computational tools that enable us to do things and to be, very bold in our ambitions on what we're hoping to see, to discover, and how to turn that and create something new, a new technology, a new entity, a new understanding.
I love that connection, not just between the approaches and the tools that you use to study things at the molecular level, but also the spirit of thinking big. Paul, I'm going to go to your thumbs up because I think you also look at things on the nanoscale level. So
that's right.
What similarities do you see there?
Similarities that I see in Gabriella's work is that we care a great deal about the nanoscale structure of systems that we build. We work with polymers. Some of them are natural polymers, that some of which are generated by our bodies or by plants, like polysaccharides, and proteins. And we deliver proteins. But also, in the technique that we've used, we've also adapted it to systems that can harvest energy in a quite different way, but which also rely on solar mechanisms.
All right. And Joanne, I know you work on plants as well, so I was expecting to see your thumbs up.
Yeah, I was going to ask Gabriella if she ever worked in my lab, because it sounds like you have. I don't know, like maybe we did a collaboration 10 years ago or something. But anyway, yeah, we're interested in those same things and how the environment, how changes in the environment in particular, can cause a plant to look quite different. And so it becomes either a longer or shorter, or a whole bunch of other things have to happen because the plant is optimizing itself to an environment from which it can't escape, right? And so that's what goes on there. And so we're interested in those same cell types that Gabriella's been interested in. And, one of those cell types I think of as the kamikaze pilot of the leaf, where they all sacrifice themselves, the palisade mesophyll up at the top, right? And so I think those cells are there to just take it for the whole leaf, take it for the team, guys. And, they have to do that. And we're trying to understand how they're different than the other photosynthetic cells in the leaf. So anyways.
All right, well, let's move to our next simple science here. And Paula, you're up. You study how to make new kinds of extra thin stuff, one layer at a time. We can use that stuff for lots of things, from helping people when we're sick to storing power for machines. So stuff is obviously an oversimplification here. So tell us a little bit more.
All right. In our work, we actually use a way of alternating positively charged nanoscale things, extremely small things, with negatively charged extremely small things. And in our case, the things are large polymers, these large macromolecules that can take on any range of function. In some cases, we're also introducing other nanomaterials. In my earlier work, we would introduce tiny carbon nanotubes, which can actually conduct electricity. We can also introduce a range of different tiny nanomaterials like quantum dots. And these kinds of materials together can help to generate things like a solar cell that can collect light. However, in our or a battery electrode. However, in our more recent work, we've really been focused on using a polymer or a macromolecule that can degrade combined with a material that we want to deliver as a drug. And so some of those are proteins, some of them are RNA and DNA, the sort of molecule of life, so that we can deliver something that can encode for a protein that will help us. And some of the things that we're working to address include creating extremely thin films that coat a biomedical implant. And if on that biomedical implant, maybe it's a bone implant, we want to grow bone around it, we can do that. Or we can replace bone when we have a big piece of bone that may be missing in a patient that maybe experienced trauma or a child that may have a birth defect. We can help to generate bone from the body's own stem cells using these kinds of coatings. We've also used this to deliver drugs through tiny little microneedles that can get into the skin but won't cause any pain. And we can deliver vaccines using DNA or RNA that way. But the thing that I'm most excited about more recently is that we've been coating even smaller things. We've been coating nanoparticles themselves, particles that are like 1/10,000th to 1/1000th of a human hair. And we can coat them with positively and then negatively charged materials. And the ones that we use actually contain siRNA that can turn off the defense mechanisms of cancer cells by silencing the genes that are really problematic in those cancer cells and keep them from responding to chemo. And in the inside, we can put a chemo drug, or we can deliver something that helps arm the immune system in the same way and gets the immune system to fight the cancer.
That's incredible. So thumbs up, thumbs down on finding connections. All right, Janet, I'm going to throw it to you first because I think your connection might be the most surprising here.
Well, it is pretty far away, but it circles back in that we also keep, as a scientist, trying to drill down further and further to understand more basic mechanistic explanations. At the same time, since I'm studying, language acquisition in infants, keeping a sense of what the whole is that they're developing within the WHOLE. But just so I think that's something that we probably all share, is trying to understand mechanism. And then as well, there are actually some specific aspects of touching. And one of them is that in collaboration with geneticists and neuroscientists, I have looked at the role of gene expression in various aspects of even speech perception development and how that might be, how gene expression can be affected by different environments, including pharmacological environments, and then down into, again, in collaboration with neuroscientists who work with animals rather than humans, down into sort of the molecular processes that turn on gene expression that lead to the circuits that we study for understanding plasticity. So,
Love
little
it.
intersection there. Yeah.
And so just to kind of offer a little bit more explanation there, when you're talking about gene expression, that means not just which genes are present or absent, but to what degree are genes turned off and on, so different levels of those genes. And that made me think, Joanne, about some of your work, because I think I see connections to what I know about the work that you do in plants.
Yeah. Yeah, we know that thousands of genes are regulated by light, right? It's just a small change in the light environment of the plant. So how can you take 30,000 genes and find the 5,000 that are going to make a difference, right? And how much difference do you have to have in the differential expression of those genes in order to see an effect on the plant in terms of growth and development? So, anyways, it's a really hard question. And when we first were working on this many years ago, when I went out on the job market, I think, in 1987 or something. And so, and I just said, I'm going to find mutants in these pathways, and it's all going to just fit together in a nice linear pathway. That was so naive, but we did it, we found our mutants didn't fit together into a nice linear pathway. And, we worked on it for the next 30 years. And we figured some of those pathways out, but we've now moved on to do some other stuff in my lab. So we're no longer working on that.
All right.
But it's a fascinating question.
Yeah, we'll come back to some of that other stuff that you're working on.
Okay.
Let's move to Janet now. You study how children learn the sounds of language and how their brains change. Your work helps us understand how we grow and how we are the same or different from each other. And I think what's really fascinating here that, at this simple level, it sounds so intuitive, and yet the techniques that you've applied to this work have really given us an understanding that goes much, much deeper. So please tell us a little bit more about how you do that work.
Yeah, sure. So we study primarily babies. So infants from birth up to about 24 months are who we primarily work with, and sometimes in utero as well. And as you might imagine, when you are working with babies, you can't say, okay, so what did you think about that? Because they don't answer your questions. And you can't give them instructions because they won't follow them. So you have to use indirect methods to try to understand what's going on in a baby's brain and how it's changing across time, like when they're growing up in one language environment or another. And so we use a number of indirect methods depending upon the age of the baby. If we want to use behavioral techniques, which I always want to do in combination with neural measures, we take advantage of what the baby can do at that age. So a newborn baby can suck. They have a sucking reflex. And you can record that and determine how it changes as a function of one type of stimulus, one type of sound or another. As they get a little bit older, they'll look reliably when they're interested in something. So you can use looking time. They'll even look at a picture when they're listening to sounds, and you can use their looking to that picture as an index of the sounds they can discriminate, or later, whether they know the word, etc. And as they get a little bit older, they can reach. So we use those kinds of techniques. And then for imaging the brain, we use, they're babies, they're precious. We use non-invasive techniques where we're measuring from the skull. And so we might measure electrical activity, encephalography, or event-related potentials. We use functional near-infrared spectroscopy a lot, which is where you shine light on the brain and it gets differentially absorbed by oxygenated and deoxygenated blood, and you can record changes in metabolic processes and how active the brain is. Yeah, and then as I said, I collaborate with people who work with animals and things so that they can drill down more into the circuits. Yeah.
All right, thumbs up, thumbs down for connections here. All right, Gabrielle, I'm going to turn it to you first.
All right. Well, there are many connections, but I'll just highlight one. The IR differential spectroscopy is in many ways related to some of the spectroscopies that we use in my lab, where we do a differential absorption measurement on plants in the visible region to look at the absorption of light and the subsequent dynamics following that absorption.
Oh, fascinating. So similar tools, different subjects.
Different
How about you, Mary?
the electromagnetic spectrum too.
Mary, what's your connection?
Yeah, I was going to do the connection more of, I think Janet pointed out something that I think we all sort of are implicitly have, but no one's saying, is that we have what we would call a macro scale response that we're either looking at or going after, trying to observe or create. And in Janet's case, it was the observable behavior of a child. In my case, it might be measuring the mechanical properties of what could look like a black box. But what you're really interested in is what's going on inside.
That's right.
Inside the head, in the brain, in the body. In Janet's case, but here in I think in many of the others of us is we're looking at, say, the structure of the material or the entity that we're looking at, wanting to know its molecular or nanoscale structure, and then how does that mechanistically give that observable, macroscopically observable response. And so I think there were some words Janet used earlier that we've all had implicit is mechanistic understanding, because that's really ties that molecular level up to the observable, by macroscopically observable. So I think there's a lot of connections in how we're able to do all those scales. And as I said earlier, years ago, people worked at one scale or the other. They weren't really able to connect these, and how we're able to really sort of synthesize these different length scale perspectives of a certain property or attribute is really remarkable now.
Mary, I actually jumped ahead as you were talking because I was getting excited with the connections to Joanne's work. So, because I think Joanne's work, again, really encompasses how you're answering these questions at all of these different scales. So, Joanne, our simple version of your work here is that you study, again, how these green living things sense light and then change what they do. And your work can make these living things grow bigger and deeper into the ground so they can help us keep Earth from getting warmer. So interpret that for us as we think about how we go from the molecular to the global scale of climate change.
Okay. The global scale is really huge. I learned that for sure. Because, I mean, people drop zeros all the time, when you're talking gigatons. But anyways. How can we do that? Well, we think we can do this because plants have not been selected for, especially the crop plants that we eat, have not been selected for traits such as making deep roots that will anchor the plant deep down into the ground and things. And so we figure we're going to be the Olympic coaches for plants. So plants are really good at sucking up CO2. That's what they do. They've evolved over 450 million years to do that. And so let me get my thoughts together here. But anyways, what we're helping the plants to do is to do that just slightly more efficiently with the CO2 and suck it out of the air and fix it into not sugars, like cellulose, which break down quite fast in the soil by soil microbes, but by actually putting them into other polymers. So here we get back to polymers again. And so, and so plants make some really big polymers that act as carbon storage devices, right? And so what we wanted to do is make the plant like kind of redistribute some of the stuff that it used to put in cellulose into this compound called suberin. And suberin is this big kind of carbon storage molecule. It has hundreds of carbons in it. And so it's a really pretty cool system. So I think if you get a few people put their heads together, you can actually work on big projects, projects that are bigger than any one lab. Because we needed to do that because we had to involve a lot of people in this because we have to. And we're also learning we have to become politicians at some level, right? Because in order to have a business model that works around carbon, you need to have a way of generating carbon credits or something like that. Right? You can't just be the Microsofts of the world or the Amazons. You have to be able to sell carbon credits to farmers, and other family-run businesses. And so, this has us going out and talking to all sorts of different people. Some of my favorite groups to talk to are the garden clubs. I go around and talk to all sorts of garden clubs, and I get people interested in our project about sequestering carbon down deep in the soil where there aren't many microbes to break down the carbon that we're asking the plant to fix for us. So anyways,
Yeah,
it's a
so
fun
that's so
project.
interesting.
It's
We've
totally
got
challenging.
polymers, we've got gardening, we've got climate change. Thumbs up, thumbs down on connections here. All right, Paula, what's your connection?
Well, Joanne said it. It's polymers to begin with. And naturally occurring ones, we use a lot of the polysaccharides, charged polysaccharides that you would find in a plant. We use a number of polymers that are RNA and DNA, but the polymer link is definitely one of the biggest ones.
And Gabriella, what's your connection here?
I mean, I think we're both interested in understanding plants, how they grow, and how they respond to different conditions. Maybe at different length scales, but as we've discussed, all of our work touches on many different scales.
All right, and then last but not least, Mary, you study the way that soft stuff can stretch and spring back by trying to understand how its building blocks hang together inside. Your work leads to new things that people use, from everyday shoes to walls that block sound. So you started giving us a little bit more insight into your work before. Help us understand what it is that you do, to the kind of techniques you use and maybe some of the connections that you've heard.
Yeah, so my work really it involves a combination of experiments, microstructure analysis, as well as computational modeling to really understand how what you refer to there as the building blocks. I have to learn this, whatever 1,000 word that we're allowed to use. I never heard of that before, but but how the building blocks really enable entirely new behavior, mechanical behavior. So if you're able to start at the molecular level, and what's exciting about working on materials that can really undergo large deformations, really macroscopic, you can see the stretching of it, is they're very nonlinear. So we talked about, there are some others here talking about putting some things together, but it's really when you have nonlinear behavior, when you then combine more than one type of material together, you get a behavior that is totally different, right? That you're able to activate say you have two different materials that you're putting together at a microstructural scale. The presence of the other material activates a different response in the neighboring material. It may activate an instability that then gives you totally different mechanical macroscopic behavior. So, so that was about the. I think you have something there about blocking sound. We found that we could, by putting these two different materials together in special geometric forms, that you could create through deformation a change in the in what's called the band gap, and what sort of sound wave could travel through the material when it's not deformed, and then totally change that with just a little bit of deformation. So you're getting these very what we call non-linear effects. Now I get too technical. See, I would never be able to do this 1,000-word test. But the sense of being able to create a whole new material. And so we've also moved into new fabrication techniques. You can now do 3D printing of materials, not just of objects, but of materials at a very, very small scale, putting multiple materials together. So you can actually design the specific geometry to really explore a whole new areas. And so there's, many of us now call this that the material itself becomes the device. Right. Paula will know what I'm meaning here, is that we used to think, oh, we're going to make some materials, and from those materials we'll make a device. Now it's like you can actually engineer the structure of the material such that the material is the device. Wow. And I think this is a whole exciting new area in mechanics, in materials, and chemistry. So anyway, I'll stop there.
All right, thumbs up, thumbs down for connections. Janet, I can't wait to hear your connection.
Well, actually, there are many, but I'll give the most concrete one, which is that I need sound attenuated environments. I need environments that block the external sound from coming in to do my research on language and speech processing. And so one of the first new domains I had to start learning when I became a scientist is which kinds of different materials to put next to one another before I could afford to buy the sound attenuated booths on the market. So, wow.
and now you can do that at the micro scale.
Wow, my goodness. Yeah.
And Paula, obviously you have some connections to this. Can you tell us a little bit more?
Absolutely. The materials that we use are also polymeric, these long chain systems that give you these really interesting properties. And, we actually take advantage of some of the same characteristics that Mary was describing around microstructure to design materials that may have a natural porosity when we process them in a certain way. And that gives us some control over how that material system will, in our case, release a drug, or how they may act in a device that might be for a battery, where you're trying to insulate something else like conductivity. So we have
you're really designing the material in a very precise way to carry out a particular function.
Yes.
That's right, exactly.
Very cool. All right, well, now that we've learned a little bit more about your research and the connections that all of you found between them, we're going to do something a little bit more fun here. Not that science isn't fun, but obviously our science is always driven by who we are and the stories that we bring with us. And so we want to do a fun little exercise with you called Object Stories. And prior to tonight, we sent each of you an object in the mail that you were not expecting. And so what I'd like to do is quickly go around and ask you to show us what the object that you received in the mail and why you think we sent that to you. So Mary, I'm going to start with you.
Okay. All right. Can you see this?
Mm-hmm.
Yes, it looks like a dress pattern. So
okay,
you can sew your own dress.
This is yes. So so it's an interesting thing. Is I spoke earlier that math and physics is really what drove me into eventually engineering. And after I I was in engineering, one of my design colleagues noticed sort of how I kind of annotate and I will do little drawings and stuff. And then he asked me, did I sew? I thought, what an odd thing. And I said, oh, well, I grew up sort of designing and sewing my own clothes in high school. And he said, you're like a designer. You're a maker. And I never saw that part of me as being the engineering part. I always saw math and physics. And I have to say, the number of women, I don't know if this what's going to happen here today, the number of women faculty colleagues that I have found had at some point, sewn some of their own clothes, designed and sewn clothes was really pretty remarkable. So I don't think we really acknowledge that in our younger selves and high school students out there now, that there's many ways that you can be a maker, an innovator, a designer, and there's a lot of spatial reasoning. So I think that's why I got this pattern.
Absolutely. Did anybody else sew their own clothes? I will raise my hand.
It could be the mechanical engineer part too. There's a very big spatial intelligence there.
Gabriella, what did we send you?
I got this keychain of the heart, which is one of the most famous exhibits at the Franklin Institute. And I think you sent it to me because I shared a story about how it's my daughter's favorite part of the Franklin Institute. And actually, my father has memories of going and walking through the heart in the late 50s on a school field trip. So it's now been 3 generations of walking through the heart at the Franklin Institute.
We always love stories about how, science museums can be a place that inspires people to come together around science. And so, to really hear how that has been this generational connection for you was something that we thought was just very, very cool.
Yeah, I actually grew up in Philadelphia, so went through the heart frequently as a child.
Janet, what did we send you?
You sent me a praying mantis.
And I will tell you that was very funny to write down on the customs form to ship to Canada. What's your story, Janet?
Well, my story, as I told you, I had wanted to be an ethologist who studies animals in their natural environment when I was a teenager. And that's actually why I study babies and language acquisition, because that's our natural environment, is to learn a language. But even before I knew about the kinds of books and the term ethology or anything like that, I was always collecting animals or watching animals. And every summer, I would capture for a few days, a praying mantis. Because I don't know if you've ever seen a praying mantis, but they look like they're interacting with you. They look at you, they kind of raise a leg, and so I loved them. And every year I would get one and just keep it. For a few days, I didn't want it to die. And every year I would name them Herbie. And so that was one of my earliest sort of forays into studying how different species, the environments that they grew up in. I think that's why you sent me this, because I told Beth that story and the whole team.
Thank you. Joanne, what was your surprise object?
My surprise object was za'atar. I don't know if any of you have ever had this, but this is a Lebanese blend, which is what my background is ethnically. And so this one has in it sumac, coriander, and sesame seeds. And you put it on salad or on eggs and things like that when you cook Lebanese food. So I guess you sent it to me because you figured only a Lebanese person could screw up the spelling of her name so bad as that my family has managed to do. But anyways,
No, we really appreciated, learning about your family story and how, how again, all our family's cultural traditions influence who we are and how that shapes us. And so we really wanted to, to honor, heritage through the way, things that we all love, which is food.
Yeah, certainly loves that. It's really good.
All right, Paula, what was your surprise object?
My surprise object was the snow globe of the city of Detroit. Yes. And I am from Detroit, born and raised, and very proud of that. And I think you sent it to me because I will often talk about growing up as a child in Detroit. It was a unique setting for me. And, it is, especially at that time, largely African-American city in terms of population. And my parents were very unique as well. My father had a PhD in biochemistry, was not the norm at the time for, this is, the 60s. My mother actually launched a nursing program. She had a master's in nursing. She launched a nursing program at Wayne County Community College, which was the first city nursing program that was available. And that really enabled a large number of women of color to get jobs that were really high paying jobs at the time. So I had this influence of being surrounded by the Black community and having a great deal of a large number of role models of other families like ours. And that really inspired me. It made me think that there's nothing that I can't do. There are no barriers. And it also made me feel very connected, both to the African American community, but in general, made me feel that I was an agent in my community. And I think that sense of enablement is something that I was able to take with me as I went on. And I live in Boston now. I love Boston, but there's always some Detroit in me. So
I love that sentiment, Paula. And that really takes us to our last round of lightning round question, which is this, and you'll hold up your other card here, is that one word that other people use to describe you is, what do we got? Relentless, passionate, determined, optimistic, and curious and creative. And what an exciting set of adjectives. Oh, and persistent. So we've got persistent, determined, relentless. I can't wait to meet all of you. Passionate, optimistic. What an energizing group of people you are. This is amazing. So as we wrap up our conversation tonight, we want to end on a little bit of an advice column. So especially thinking about that word that people use to describe you, what is a piece of advice that you would tell a young person who is curious about science and how to find their place in that? And Paul, I'll kick it back to you to get us started with this question.
All right. And my word was optimistic. And I think that is something that has helped me. And I would advise a young person to keep in mind at all times that there is always going to be some sort of challenge that they face, but there will also always be the opportunity to overcome challenge. And this is true when you are studying, you're trying to learn what you need to learn. Don't let go of the dream. Keep in mind that big picture of who you want to be in the future. And for me, that's, I always think when something's going wrong, well, we can always find another way. We will get there. And if we don't get there, there's probably something else that I need to pursue that is even better. And I think if you keep that attitude in mind and you allow yourself the room to give yourself credit that you are an amazing person, that you have a huge skill set and a lot to bring, no matter what you're feeling at the time, then you'll be fine.
Wonderful. Joanne, you described yourself, I believe, as relentless. Tell us a little bit more about some advice that you might give somebody that channels that characteristic.
Well, I don't know. I mean, I think I just have never really given up on issues. So optimistic is just a more positive way of describing it, I guess. I don't know. But anyways, I don't know. My son-in-law calls me sassy Situ. So Situ is the Arabic word for grandmother, right? So I grew up in Boston, so I think I come with that edge. And I live in San Diego now, right? And so for the last 36 years I've lived here, longer than I ever lived on the East Coast. But anyways, I'm still bring a little Boston to me wherever I go, the way you bring to Detroit, Paula. Anyways, it's kind of funny. But yeah. So in terms of science, I don't know what to say. You know, I think if you love science, you'll find a way to do it. So
be relentless.
Be relentless, that's right. And remember that you can make a difference in the world. And I think that's something kids have forgotten. I don't know. I get a little worried about it because I just really felt like I was enabled by college, at a liberal arts college, you know, to take on the world and do something that might make it a different place. So
I think that's a challenge to any kids at the audience today.
I know, because partly because universities are so big and you don't get to know your professors and stuff. You know, I can see a lot of issues that could be made better for the student. But anyways, we
That's
can
a
talk
great
about that another day.
Yeah, just to seek out the people who inspire you.
Yeah.
Janet, you described yourself as optimistic.
I described myself as passionate.
Passionate.
So,
oh, sorry. I misremembered.
Yeah. I hope also optimistic. But so I think what I would tell a young person is to follow your passions. And the questions that excite you, the areas, you know, that excite you, to try to find a way to make that your life if it excites you that much, from when you're first getting started to the new experiments you do across your career, and the new opportunities. And yes, when you're passionate about something, you make the people around you passionate about it as well. So whether you're teaching or mentoring, and then to find that path, in my case, it was teachers and mentors who were incredibly important. So I come from a small town in Kansas. I had a biology teacher in high school. When he heard what I wanted to do, he helped me get a scholarship to work in the kitchen, so I could go to a biology field station as a high school student, and that was phenomenal. And at that biology field station, I became friends with the daughters. There were 5 daughters of one of the profs who was there, and he then took an interest in me because I was, hanging out with all his daughters, and when he understood what I was interested in, he said, okay, we're going to take a family vacation. We're going to take you to Cornell, because that's where he had done his PhD. And I'm going to introduce you to the bird lab there, so you can learn about studying animals in their natural environment. So they did that. I went home. I flew from small town Kansas to Indianapolis. I went with them on a driving vacation to Ithaca. And that's where I started my undergraduate university. So, but then part of the passion is we're not just scientists. There are other things that we're passionate about. And I would tell a young person as well, is to feed those other parts of your soul. And for me, that's exercise and music and, being with people I love. And so, but whatever it is, yeah.
Yeah, that's so important to remember, to be yourself in all of the ways of the word.
Yeah.
Gabriella, you were optimistic.
I was actually determined.
Oh my goodness! Now I'm getting confused. Who was optimistic?
Paula was optimistic.
Oh, you were optimistic.
Right. Yeah.
I'm not sure I describe myself as optimistic. My advice would be to follow your curiosity. And I think that's where my determination comes from, because when it's my curiosity and what I want to know, that becomes so motivating. So that's my advice.
So find what it is that really drives you, and that kind of innate motivation keeps you going through the hard times.
Yeah, what you're curious about the world around you, or what you're curious about that you want to create. What is your scientific curiosity?
Yeah, because science is not always easy, so maybe it can't always be optimistic. And Mary, close us out here. You're curious, creative.
Yeah, so I had curious, creative, and persistent. So I broke the rule. I didn't just put one. But I think, my advice is to really never lose your curiosity. That, as Paula had said, you sometimes run into brick walls, and you've got to figure out how to get over them. And I think if you maintain your curiosity and that spirit of really discovering and persisting and going after something, and being open that there could be a different path, right? That there's more things to learn, to always be learning, always be open to learning, always have your curiosity there, and remember what gives you joy, right? That I think scientists and engineers, I think we have a job that gives us joy, that we don't even think of it as a job, right? And I think it's because we're always able to have our mind open, and to be pursuing something new. And I want to echo about the having a mentor. It may not be a mentor, but taking some opportunity to do some research at every stage. And I think that's what Janet was pointing to. And it can also, if you're in this big university, my undergrad was at a big state university, Virginia Tech, but I did 2 independent research projects, and it changed my life. And so I think you can always find your way, but you also have to be looking for it, and you have to be going after it. So it's find your joy, maintain your curiosity and your creativity, because that's actually what's at the heart of being a scientist and an engineer to me.
Well, what a wonderful group of people to give advice to anybody who's thinking of any age. I mean, I'm inspired all over again listening to all of you. I wanted to thank you first to the 5 of you for joining us tonight. We are very excited to have you here in Philadelphia in person next week. A little look ahead to what else is coming. This is really just the launch of our Awards Week celebrations. For anybody who's out there locally, we hope you'll join us for a live in-person program at the Franklin Institute on science and cooking with another one of our laureates, Dr. David Waits, and Chef Nock from the acclaimed restaurant Kalea. In addition, for those of you joining us virtually tonight, we hope you'll also tune in for the live stream of the awards ceremony next Thursday night. And more details on both of those programs are available on our website at www.fi.edu. So thank you again to our laureates who have joined us here tonight. What a wonderful conversation and dialogue. And we appreciate all of you. You're really sharing your work and your passions and your advice with us, to inspire future generations of scientists who are out there. And thank you to all of you who joined us in the audience for being part of our celebration of these incredible scientists and the way that they are transforming the world. Thank you all, and have a wonderful evening.
Thank you.
Good night.